So we have seen the synchronization hardwares. In hardwares, I have already told you that we have seen the memory barrier, which means that actually memory barrier is under the hardware synchronization, but it was it is actually misplaced in this slides. However, to see the correct order, you go to the book chapter number 6 to see the correct order of this hardware synchronization. Okay, so memory barrier lies under the hardware instructions and under the hardware approaches. Okay, and also we have some hardware instructions, which means that we make sure the synchronization by some hardware approaches. However, the uniprocessor, we have seen that it is not applicable or not feasible in current situations. Okay, so we are proceeding with the hardware instructions now. In hardware instructions, we have two type of instructions. Okay, we have some test and set instructions and some compare instruction. So a special hardware instruction that allows us to either test and set and modify the content of a word or swap the content of a word uninterruptibly. It means, which means that atomically. Okay, so these are to the instruction sets of hardware approach. Okay, now before proceeding, I must also tell you that there is a lock, right? There is a lock which is actually alternative to hardware approach. We can say that a code might be, let's say, while this is true, then acquire a lock, okay, and the critical section will be executed here. The critical section goes here. When this critical section is over, then release the lock. This is also called the Mutex Lock. Okay, so remainder section goes here. Okay, so this is actually an alternative approach. Now in test and set, we will be using this lock also. You will be seeing this, you will be able to see this lock also. Okay, this is not hardware solution, but this is actually used in the hardware instruction set. Okay, so modern machines provide special atomic hardware instructions like test and set and compare and swap. In test and set, you check the value and set the temporary value, set the value to the another temporary variable, and in compare and swap, you actually compare two values and swap them in between. Okay, so here, right, here we see that here we can see that we have a target variable, a target pointer, right, and we have a RV pointer. The target is actually, that value of target is assigned to the RV, and then target is made to true, and then return the RV. So the original value is RV, but it is the original value is shifted to RV and the target has changed. It means that if this instruction is even in use in some other processes, it can still preserve the same value. Okay, it can retrieve the same value. So this is a target test and set value. Okay, it is executed atomically and returns the original value passed of the parameters and set the new value of the parameter. It means that even if after execution, if we want to access this variable, then still we can retrieve the original variable value. Okay, from this parameter. And as I have already told you that there is a lock condition also, so that we can put a lock on some test and set conditions like this. And the lock is first initialized to false. Let me select the pane here. Now here, if we see that this is the same test and set, but we check this through the lock, either if it's locked or not. If it is not locked then the critical section will never come, right? If it's not, if it's locked, then the critical section will execute, okay, and if not locked, then it will keep on spinning here, okay. This is same the before software approach we have seen, right? So this is a waiting state, and this is again the release of the resources. Once this is done, once this is false, and if the lock, if the critical section is over, right, if it's over, then the lock is made to false and the remainder section will be executed here. So we have also some other approach of compare and swap. For example, if I will actually make some very simple example for you guys here, that for example, if we have a wide and swap method here, and I say that boolean A and boolean B, these are two pointers, right? And boolean temp takes the value of A pointer, right? It points to the A, and the A is replaced with the value of B, right? Now B, this is actually asterisk, okay. The now B is equals to the value of 10. So this operation is performed atomically. This executes atomically, okay, inside this. Now here this should also execute atomically, as we have seen that this operation should also execute atomically. Then we inserted the lock here, okay. The lock ensures that once it's in critical section, it's doing something, if it's testing, then it cannot set the value, okay. When it's setting, it's again in the critical section. Similarly here, compare swap, we have seen that there's a problem. This is the problem actually, that we have to compare, we have to see if we have to actually swap the contents of A and B, where the value of A is assigned to B and the value of B is assigned to A. So this should be also atomic. To do this, we have also lock here, where we set the lock here, okay. We have lock here. We when we are executing this, we lock the instructions, and when we release this lock, then the remainder section only can execute. So we have also some bounded compare. While this actually depth is not required in this topic, okay, you must know that in the hardware approach we have some locks which are actually not the hardware approach, but which are used with the hardware approaches, okay. So the instruction sets we have seen is compare and swap, and also test and set, okay. So we have also some atomic variables, and similarly here atomic variable is also shown with the in this compare and swap example, okay. This here is the compare and swap example. So this is another example of this. Now we have mutex locks, as I have already told you that okay. Now before proceeding, I must show you that there are two type of actually synchronizations, right? There are two approaches of synchronization. One is either busy waiting, and other is no busy waiting. Now one of these mechanism, from these mechanism, okay, I must write here the mechanism. The working of this synchronization is, the first one is busy waiting, another is no busy waiting. Okay, now in busy waiting, what happens that if P1 is in critical section, then P2 keeps on trying. This is trying, keeps on trying. Or we also have spin lock. The term for this is spin lock, which means that this here is stuck and it is keep on spinning. So this thing is called, this mechanism is called spin lock. Okay, so if P2 is trying, then it is waiting, but it is busy, which means that it is consuming some CPU here. Okay, alternatively we have no busy waiting, where if P1 is in its critical section, then P2 goes to sleep. Okay, it does not keep on trying. P2 goes to sleep. Okay, and when this over, this come here to wake up the P2. Okay, so this is the no busy waiting, and this is more CPU efficient. Okay, so you use actually CPU very efficiently here, right? And here the CPU usage is inefficient. But as this approach reduces the overhead of PCB, so this also keeps account in several situations. Now here the Mutex lock, as I have already told you, that I have already before explaining the compare swap and the set and test hardware instructions, I have already told you that there is a lock, right? That's called Mutex lock, which actually acquire when it enters. Okay, when it enters into. For now, for suppose if this is the critical section, right, and then there is a lock. Maybe I cannot draw very well, but assume that you can understand that there is a lock. Okay, now if P1 and P2 and maybe we have Pn, right, Pn tries to access, then if this is not ready and this is not ready, this guy is ready, then it will first come here, and the lock is open. For suppose now the lock is open here, right? When it goes into the critical section, then it will close the lock, right? It will close lock, it will do its work, okay, finish its works, and when it is exiting, it opens the lock, okay, release the lock, and then only the new process can come. Otherwise, if this is closed, then if both processes are trying but the critical section is actually locked, so they cannot enter into the critical section. So this is called the Mutex lock. Okay, now to tell you that how actually Mutex lock works in some code, that for example if there's int x and we have a Mutex lock and we lock the variable a, oh sorry, x, here x, if we lock the variable x and then void procedure, maybe any procedure, right, and we initiate that, okay, there might be some any variable, okay, we can say that mutex lock and lock x, okay, and then we manipulate. Okay, once the manipulation is complete, the mutex lock is, the mutex is unlocked actually. Unlock, okay, the mutex is unlock the lock x, okay, x lock is released. Similarly, if for the other guy there will be a lock, if it will check if there is a lock, then it will be it will be waiting. When the lock is released, it can enter into the memory, the shared memory space. Now we have another approach also. There is semaphore. Semaphore is also another approach other than the mutex locks. This is a different approach, but there are actually two flavors of the semaphore. Okay, the first flavor is binary semaphore, where we have two values, two processes, which is for only two processes, and then another is counting semaphore. So we have two type of semaphores. Binary and counting. This can be any number, right? Any number of processes, right? And this is only two, for only two processes. It means 0, either 1, either the P0 will go or P1 will go into it. Okay, so this actually may allow more than one processes. More than one processes. Okay, okay, so now semaphore, what is now the beauty of semaphore is that this all is handled, this control of the concurrency of this control is actually managed by a single integer variable. So we don't need to have a heavy programming here, but we can deal with simple integer. Okay, we can manage this by a simple integer semaphore s, right? So this integer semaphore is represented by s. Sorry, now I'm sorry for the calling I'm receiving in between this lecture. I have already made my mobiles on silent, so I hope that this will not interrupt. So now this s integer is actually there to do all the magic. Now this s is when 0, then this means that one can enter, or if it's 1, then maybe one cannot enter. Okay, so these two, because there are two values of s, so we say that it is a binary semaphore. Okay, now this can be accessed by two operations, the wait and the signal. Also these operations are represented by p of s and v of s. Usually we write this like this, p of s and v of s. Okay, this p means that wait, and this v means signal. This signal is for another process to wake up. Okay, so okay, now for wait, if we say that p of s while s equals to 0, this will make this stuck. Okay, or keep on spinning. or maybe busy waiting. This is actually the example of busy waiting also. Until now, whatever approaches we have seen, these are actually busy waiting. Next approach, this in semaphore, the counting semaphores are actually non-busy, no busy waiting approach. Okay, so I believe that that approach is the best approach, the counting semaphore. So this P of S is here, and while S equals to 0, then keep on spinning, and once it's S minus 1. Okay, so the same thing is actually here, but this is something complicated, so I made it simple here, simplify it here. Okay, this is the same version, same thing, but with new version. Okay, so this is much simpler for you guys. And on the signal side, we have nothing but we have V, as I already told you that when it's over, then it will give a signal and it will increment the S value by 1. Okay, so initially the value of S is 1. Why this is 1? Because if this is 0, initially if this is 0 and it is decremented by 1, then it will go into the minus 1. This minus 1 actually represents the block list. So as this binary semaphores doesn't have a block list, so we initialize this with 1. Even if some have block list, we still initialize them with the maximum number of the processes. So as we have only 2 number of processes, so we initialize this S variable with 1. Okay, because 0 and 1 are 2 processes. If we have 5 processes in counting semaphore, then we will initialize this S with 5. Okay, so the simple thing is that this is the implementation of V and this is the implementation of P. Now for suppose if I can write some, if there is some blank slides I can insert, I can make this explanation more for you guys. So I hope you have seen this this implementation, then I can just remove this and I just proceed with some example. Now for example, we are on the same slide but we are considering an example. Now for example, if there is a program, right, maybe we say a process 1 and process 2, and this is the critical section. Okay, now if S equals to 0, then maybe this process can enter into the critical section. Okay, so here is the P1 is into the critical section. So when this P1 releases the resources, it make this to 1. Okay, so that this process now can enter into the critical section, and when this will release, it will again make it 0. Okay, so how this actually works? For example, if there is a program, right, and here is the code, right, some code goes like this. Okay, some portion of code goes here maybe, and then we have P of S, then there come the critical section. Okay, here it will decrement this by 1. Okay, when it is over, then B of S is executed, as we have already seen the implementation of P of S and B of S, and once it is over, then the remaining section will come. Okay, so this is just an example that how these are actually implemented. These two functions of atomicity operations are implemented. So we have counting semaphores and we have binary semaphores. I already told you that counting semaphores are when we have more than one processes are which can enter into the critical section, and the binary semaphore when we have only 2 processes which can enter into the critical section. Now now the binary semaphores works similarly, as we have already seen that on the entrance it locks and on the release it releases the lock. Okay, so these actually work similarly like Mutex Lock, but the counting semaphores are different, right? How these actually counting semaphores works? These are actually okay. How these counting semaphores actually works, I must show you by drawing some example here. Okay, for example, if I have P1, an array of processes P1, P2, P3, P4 and P5. If I have an array of processes and this array can go into the now the critical section can actually handle, this is critical section. Now the critical section can actually handle more than one processes. Okay, let's say it can handle 5. The length of this critical section is applicable for 5 processes. So what will happen, we will initialize the ACE, means semaphore variable, to maybe 5, right? Maybe if we are starting from 0. However, when we are programming, we always start from 0, but in this I have considered to map this with the same numbers. Okay, so if you are starting this with 0, then here it will be end on 4 and the length of this ACE will also be 4. Okay, so however I am considering 1, 2, 3, 4, 5, so starting from 1. So now the ACE, the value of ACE, the semaphore has the capacity of 5. Now for example, if P1 will come here, now as we seen that this is this is not 0. Okay, then what we will do, we will allow this, we permit this to enter P1 into the critical section, and we apply the P of ACE here, which means that we decrement the ACE. Okay, we will decrement the ACE and this will become 4. Now if P2 will come, then again this will be decremented to 3 and P2 will be allowed. Now as P3 will come, then this will be decremented to 2 and P3 will be allowed to enter into the critical section. Now on the arrival of 4, this will be decremented to 1 and P4 will be allowed. Now arrival of P1, this will be decremented to 0 and P5 is allowed. Now we see, now the game starts here. Now as the length of critical section is over, the capacity of critical section is 5 and it is already over. Now for suppose if P6 arrives, then what will happen? Then again this P of ACE will execute here, and this 0 will be decremented to -1. Now remember that if there is a minus in the if the return number is negative, then that process which made this number to become negative would be shifted to another memory. We call it as block list. Okay, this P6 will be shifted to block list. Now this is -1. Now for suppose P7 has arrived, this will again be decremented by 1 and it will be -2. P8, P9 and P10, maybe any number of processes has arrived. These will be decrementing -3, -4 and maybe -5, right? -5. So P7, P8, P9 and P10. Now this block list is in this memory. It means that these processes are not trying. Block list means that processes in block list are actually not trying, not in a loop. They are not in a loop. They are not trying indefinitely. There is an infinite loop, while loop, where the processes keep on trying. However, in this block list, the processes which cannot get the entry into the critical section are put into the block list, so that if one of them has released the resources, V of S is done here, then what happens, that we know that V of S actually increment the S by +1, which means that now -5 would become -4, which means that now it has a capacity of 1. So one of the process, this will give a wake up call to the P6, and P6 will be allowed to enter into the critical section. Now when this will be entering into the critical section, again the P of S will be incremented. It means that it was -4, then again -1 will be applied, and this will become -5. Okay, so now we can see that how actually counting semaphores work. Okay, so we have seen the binary semaphore, and we have also seen the counting semaphore. So here is just a mutex lock is shown here, right? And this was actually the binary semaphore is the implementation of busy waiting. However, the no busy waiting comes with the counting semaphore. Okay, now in this semaphore we have two operations, as we have seen. We have block list and we have wake up, right? Block means places the process invoking the operation on the appropriate waiting queue, right? This will actually, the processes which has invoked will be put into the waiting queue. Okay, and wake up is when remove one process in the waiting queue and place it in the ready queue. I'm sorry, I have made a mistake, that when I removed one from waiting queue, and then I again applied the S of P of S. So P of S would not apply over here. Okay, so make the correction over there. In the previous slide, make the correction. Okay, P of S would not be there when the second time it is coming to the critical section. The P6, when P6 is coming to the critical section, P of S would not be implemented. Okay, because P of S would be followed by V of S. Okay, so we have a wake up call here. So this is not no busy waiting, this is with no busy waiting. Okay, now here is just the same example which I have already told you. Okay, there is a block list, there is a list where the negative, if the value is less than 0, then this will go into the negative list. If value is less than or equals to 0 and value is incrementing, then this will be retrieved from the negative list, the block list. Okay, by a wake up call. Okay, so problem with semaphore is that, for example, if the resources are actually, for example, if there is a train 1 and there is a train 2, now both of these trains are waiting for this track to be released. Okay, now if such situation comes here, then there is a situation of deadlock, right? So in semaphore, when it is used incorrectly, then a deadlock can occur. When the signal is also released and this is also not available, right? So this is a situation of deadlock, when both are waiting for each other, or both are not ready, right, or both are accessing the same resources, right, and both are not getting the resources. So such situation is semaphore is deadlock, and deadlocks cannot be avoided in semaphores also. Even in the previous approaches, software and hardware approaches, there are also deadlocks, and if the deadlocks are happening in the semaphores, if you have a question about the deadlocks, they can happen in the semaphores. Yes, they can also happen in the semaphores also. Okay, so I will explain this deadlocks in the next part. Okay.